Hello, y'all. Welcome to lesson 71 of my DP chemistry curriculum. Today we're going over reactivity 1.2.5. It's an HL topic. We're going to be covering the Born-Haber cycle, how it's an application of Hess's law used to show energy changes in the formation of an ionic compound. So we'll interpret and determine values from a Born-Haber cycle for components composed of univalent and divalent ions. So we'll talk about that as well. The cycle will include ionization energies, enthalpy of atomization, and possibly sublimation or bond enthalpies, which was cut off down here. So, with that said, let's talk about what this actually is. And we're talking about how atoms slash elements, in the case of diatomic ones, elements form salts. And when we think about that, we're really thinking about delta HF, the enthalpy of formation or standard enthalpy of formation. But well, that's from individual components. This is actually a simplification. Simplification. We can't just take solid sodium and like Na solid and one half of a chlorine diatom. Oops, what am I doing? Uh, gas and make NaCl solid. This isn't really how it works. There's a lot of steps that must happen. Bonds between the diatom must be broken. The solid sodium has to break apart from its structure and become a gas so that it can properly react. They must atomize. So what are all the little steps in between that we represent with the arrow? So for this, we actually have to look at each individual thing. We do know that the delta HF of sodium chloride, just for the record, is negative 411 kilojoules mole inverse. So we're going to keep that down there because we'll come back to it. But let's talk about the individual steps when forming the salt. So like I said, first, and I'm going to do a bunch of steps. We're going to have quite a few. First, we need solid sodium to become a gas. Now, this is because in our reaction right here, each atom of sodium reacts on its own. It's not one giant block all reacting at once. Each atom must be on its own, and an atom on its own is technically a gas because when you think about sodium, if you just pulled one atom, then it's not part of a solid shape or structure. It can float around. There's no forces interacting with it, so therefore that single atom is a gas. So how do we do this? Well, turns out we have an enthalpy for that. We actually have an enthalpy for pretty much anything. Oops, enthalpy is H, delta H, atomization. Sometimes we just refer to it as delta H atom, and that is represented by this equation, or sorry, this is the energy to turn 1 mole of solid metal or solid compound to gas. Substance, not even substance, we're going to say element to gas. So this happens with metals and nonmetals, so we're going to look at both of them. Metals are represented by the equation metal solid turns into metal gas. And the energy required to do this is always positive. It's always going to be greater than zero because we have to put energy in to break those bonds. Remember, breaking bonds is endothermic. For diatoms, which most of the time it's non-metals, and when we're dealing with salts, it's usually a diatom. We have one half of our diatom. Usually they're in their gaseous state. Most of the diatomic elements are gases. Uh, and we are breaking these apart, sorry, X2, and we're turning this just into, uh, sorry, X gas. And that is also going to have our delta H of atomization, and that is going to be also greater than zero. So we have this reaction. We're originally talking about sodium, so we're going to apply this to sodium. So I'll use blue for each of our main elements here. Therefore, Na solid reacts to form Na gas, or I guess doesn't react to form is broken into Na gas. Our delta H for this of atomization being greater than 0 is 110 kilojoules mole inverse. So that is our first step in converting. Once again, we're just really working on this equation, converting our sodium to a sodium chloride compound. So, second, our gaseous sodium must become ionized. Gaseous sodium must become a cation by losing an electron. Now, when we lose an electron, that's generally referred to through our ionization energy. Ionization energy, if you recall, is the whoops, energy required to remove 1 mole of electron from 1 mole gaseous atoms. Well, good thing sodium's already a gas. So for our metals, we generally represent it as metal gas becomes metal plus gas plus electron. This we would refer to as ionization energy 1, because this is the first ionization energy. So often we can remove more than 1 electron from a metal. This is also greater than 0. It always costs us energy. We must put it in to convert a gas into a cation. Furthermore, we can take this a little bit further. If we already have an ion, we can make it a 2 plus ion, still gas, plus an electron. This would be ionization energy 2. It's greater than 0, and also it's going to be greater than our ionization energy 1. But with this said, sodium just needs to become a 1 plus metal. Therefore, Na gas. So this is our sodium from before. This is the same sodium, and now we're just going to be converting it. It's going to be ionized to become Na gas plus an electron. The ionization energy, the first one of sodium, is found on section 7 of your data booklet, I believe, but it is 496 kilojoules mole inverse. All right, again, it's a positive value. All right, so sodium is in the state it needs to be to react. So sodium is actually good. We turned it into gas, we turned it into a ion. The next thing we have to work on is chlorine. First off, we have to break these bonds. So, third, the nonmetal must change to single atoms so we can later convert to an anion. So first we're going to change it to single atoms with this nonmetal. So we have to break the bond. This is where we have bond energy. We generally represent this with a capital E, and this is the energy required to break 1 mole of bonds. For chlorine gas, Cl2, oh, I'm doing a real equation now. For Cl2 gas, we turn it into 2Cl gas, and the energy for this of Cl2 is 242 kilojoules mole inverse. So Now our chlorine is halfway there. We just need to give it an electron. You can probably guess what we're going to use for that. Fourth, nonmetal must gain an electron to become an anion. Again, this could happen once or twice, depending on what you're using. It's kind of the inverse of ionization energy. This is electron affinity. Electron affinity, also known as EA, we haven't used it that much, is the energy released when 1 mole of electrons is added to 1 mole of gaseous atoms. So this is generally represented by the equation X gas plus electron reacts to form X gas with a negative charge. This electron affinity, because it's energy being released, is always less than zero. So far, we've had positive, oh, that's a correction up here. Bond energy is always greater than zero, as breaking bonds requires energy. It's endothermic. But electron affinity is always going to be less than zero. For our chlorine, Cl gas plus an electron reacts to form chloride gas. That chloride has an electron affinity of negative 394 kilojoules mole inverse. All these values are in the data booklet, by the way. These aren't like, I'm not pulling them out of nowhere. They're in the data booklet. All right, so we're going to take a brief pause here now that we have chlorine in the proper state and sodium in the proper state. We have these things that we have just spent all this time figuring out. Well, how do we make this original equation work? Because this is, well, let me clean this up a little. Our enthalpy of formation is not as simple as it seems. So how do we make this equation actually work? So to reiterate, we turned sodium into sodium ions in a gaseous state. We turned chlorine into chloride ions in a gaseous state. So now we have to bring them together. That's enthalpy of formation. But there's one thing we must also think about before we finish this off. So let's recall delta H lat. This was lattice enthalpy. Lattice enthalpy is generally a measure of the strength of the ionic bond. Measure of strength of ionic bond. And this is kind of the inverse of the equation, what we're looking for. NaCl solid becomes Na gas positive plus Cl minus gas. This is the inverse of what we've been trying to find. We also know that this reaction is definitely endothermic. So why am I bringing it up? Well, the reason I bring this specific thing up is because it seems like we could just take the opposite of our lattice enthalpy and figure out our formation, or figure out the actual individual steps of our formation. But the problem is we're actually going through all this trouble because lattice enthalpy itself is incredibly hard to find. While we can find all our other values, lattice enthalpy is almost impossible to find, to determine. The problem is, whenever we're determining lattice enthalpy, there are too many other factors. Too many other factors. Like if we're dissolving something in a solution, yeah, sure, we're talking about lattice enthalpy, but also there's forces of the water molecules pulling on each of the individual ions or this or that. Maybe the solution is hot or cold or something or whatever. And it's kind of impossible to get. So this whole thing, why we've done everything, is actually, like we said, an application of Hess's law. Hess's law is going to allow us to find delta H lattice through application of known enthalpy values. So we're going to create an energy cycle. Create an energy cycle to demonstrate formation of salt. This cycle is what we call the Born-Haber cycle. So let's go ahead and make this cycle. This is the entirety of the unit. This is kind of what we're really focusing on, and we're going to show it using enthalpy values. So let's start with I'm going to start, and I'll actually write my steps out. Switch over to white. Start with delta H formation. So the reaction for delta H formation we know is Na solid plus 1/2 Cl gas. And instead of going reacts to the right, I'm going to use arrows to demonstrate energy change. This reaction goes to create our salt. Our salt being NaCl solid. This is our delta HF. I'm using a down arrow because this is a negative value. We know before that this value is negative 411 kilojoules per mole. That's what we wrote all the way at the top. So delta H formation is negative value. I'm using a down arrow. Once I've written my delta H formation, I'm going to go through each steps of how we actually get there. There are intermediate steps. Our second step is we must atomize, or the first step in it is atomize our solid sodium. So when we atomize our solid sodium, we get the same reaction, but now it's Na gas plus 1/2 Cl2 gas. This is our delta H atomization. This is a positive value, so I'm using an up arrow. After we've atomized our gas, the next step was we were going to ionize sodium gas. Once again, this is a positive value, and this will give us Na gas plus 1/2 Cl2 gas. So I'm going once again up for positive values and down for negative values. Now, once we have sodium in the proper position, which it is, our step 4 was we were going to, or I guess step 3 was going to break the bond energy. What I should really do, and I'm going to take a moment to do this, is go ahead and erase these numbers and replace them with this is what we're trying to do, or this is our starting point. This is step 1. This is step 2. The reason I'm erasing these, by the way, is just to match the steps that we did here. We called these first, second, third, fourth. I'm going to try and follow that. So our real step 3 is we are going to break chlorine bond. Once again, breaking bonds is a positive enthalpy change, so we're going to use another up arrow, and this results, and we're going to need some space. Actually, whoops. Let's make sure I'm doing this properly. We forgot one thing. When we make a gas, we add an electron. Gasp. I have to make sure I keep that consistent. So now we're going to break that bond. And I'm going to put this all the way across because I'm going to start moving to the right. Nope. And I missed ionization energy 1 of sodium. All right, correcting my mistakes, we are now breaking the bond in chlorine. It took us long enough. When we break the bond in chlorine, we get Na plus gas plus no more 1/2, just Cl gas. And we still have that pesky electron hanging around, so we got to maintain it. This is going to be our energy of chlorine. Now, we can't just leave it here at the energy of chlorine. If we look at our equation for breaking chlorine, all the way up here, we're turning 1 chlorine diatom into 2 chlorine atoms. That is the energy of breaking Cl2. However, this time we're going from 1/2 of a chlorine diatom to 1 chlorine. So when we calculate the energy of breaking chlorine, we actually need half of it because we have half the amount of atoms. This 1/2 is incredibly important to our calculations, so we need to make sure we keep it consistent. All right, from there, step 4, we need to add electron to chlorine gas. That's the electron affinity. That value is negative, so now we get to use a down arrow. The question is, where does this down arrow go? And I made it too long. This down arrow, the gap between this and the electron affinity, oh, actually I made it too short. Let's double check our values. So we notice that adding an electron is about -400, while 1/2 of 242 is about 120. So this decrease is actually going to take us a little further than this past one. You will never have to draw one of these on the IB exam, by the way. You just have to be able to understand and read the steps. Once we add that electron, we're finally going to get rid of this electron right here. So we have Na gas positive plus Cl minus gas. And this is our electron affinity of chlorine. There it is. We have our Born-Haber cycle. The last part is we're going to add line for delta H lattice. Delta H lattice is this positive line. We know it's positive because taking the lattice structure and breaking it is breaking a lot of bonds, and therefore that is endothermic. Alrighty, here's our Born-Haber cycle. So how do we actually use this in conjunction with Hess's law? So this is the real struggle. But due to Hess's law, we can take any path from one point to another, and those paths have equal energy change. So I'm going to draw 2 paths here, and I'll explain why I'm choosing these paths in a moment. This is path 1. I'm going to change the thickness of that. Nope, now it's too thin. We need a happy medium. This is path 1. On the other hand, we have a secondary path, path 2. I'm choosing these for two reasons. One, we are starting from our actual starting point of the enthalpy of formation, and we're ending at what the atoms must actually be before they become sodium chloride. The other way is I'm following arrows in the direction they want to go. You'll notice that both ways I'm never going against an arrow. I'll tell you why this is important in just a moment. But the energy of path 1, energy of 1 should be equal to the energy of 2. This is what Hess's law states. It does not matter the path you take to get from one point to another, those energies are equivalent. So we're going to write out the energy of path 1. Path 1 is the delta H atom plus the ionization energy of sodium plus 1/2 of the bond energy of chlorine plus the electron affinity of chlorine. Each of these are positive because I am following the direction of the enthalpy change. So I'm adding each of these enthalpy changes to one another because I'm not going against the arrow. If I were going backwards, they would all be negative, but I'm going forwards, so they are all positive. This is therefore equal to delta H of formation plus delta H lattice. I like to keep all of my things kind of in the same general area. I like to line up my equal signs. All right, so Hess's law allows us to make this comparison. And what I mentioned at the top of this is that it's impossible to determine the lattice enthalpy experimentally. There's too many factors, but we don't need to do it experimentally when we have the others. Now we're just isolating the variables. I can rearrange my whole equation to say delta H lattice is equal to, and I'm going to shorten these, delta H atom plus ionization energy plus 1/2 bond energy plus electron affinity, and then minus delta H formation. And this will determine the lattice enthalpy of sodium chloride. I can plug in the values that we demonstrated all throughout our initial notes. So I'm going to go ahead and plug these in now. The atomization is 110 kilojoules per mole. I'm going to skip units for now. The ionization energy is 496 kilojoules per mole. 1/2 of 242 is 121 kilojoules per mole. Electron affinity is a negative value, but I'm still adding it, so minus 349. And then we're going to subtract the enthalpy of formation. The enthalpy of formation is negative 411. You'll notice I didn't go down on this lattice enthalpy because what I'm really trying to do is actually go with the equation. These arrows much less represent the positive and negative sign that I was doing before. It's just a useful tracking method. But in general, these arrows represent what is going on. Gas to gas ion, that direction is ionization energy. If we used a reverse arrow on this, we would be talking about electron affinity. All right. Finally, I plug all these values into my calculator and I get 789 kilojoules per mole for lattice enthalpy. This is how we calculate it. This is how we figure this out when we cannot do an experimental process. We use Hess's law in what we call the Born-Haber cycle. All right, so the last thing before we end this off is what affects lattice enthalpy? Remembering that lattice enthalpy is basically the strength of electrostatic forces between ions. And if it's a strength of electrostatic forces between ions, we know the answer to this. It's two things. One, the size of ions. A large ion is a weaker bond. And two, the charge of ions. Large charge is stronger bond. Once again, it all comes back to electrostatic interactions, and therefore it all comes back to two things, size and charge. So that's where I'm going to end you off here. I hope this helps you understand the Born-Haber cycle. It takes a bit of practice. You just got to do it, and have a great day.